Oh, maybe. Okay, I see a chat. Sorry. Um, I can't see the chat usually. Hi. I won't be able to see the chat anymore. All right. Um, Here we go. We had a couple of people, not everyone, which was kind of confusing, who were not able to open the assignments uh, before. Is anyone able to get that sorted? Yeah.
So I can open it on my iPad or my phone, but it works on my laptop.
Oh. Okay. I did have someone in my other class this morning with that problem, and we figured out that he had to allow access in his privacy settings. And so if it's not working still, then try that. But definitely let me know if it's not working. Like if that doesn't sort it out, then. And it kind of sounds like maybe your laptop had different privacy settings than your iPad, for example. Maybe. I don't know. I'm just making this up. I blame Steve because you guys don't know Steve, so I'm just blaming a random person. But he moved everything from one server to another, which is obviously a huge job. So good job, Steve. But also, now we're on a new server, and it seems to be kind of not working quite as nicely, but we'll get there. So do let me know. I am gifting you with many more assignments. Because today we were supposed to start chapter 3 today, and then I thought, now we'll just settle down, and we've got a little bit of wiggle room, so we'll see how that wiggle room plays out next week. That's next week's problem. So we'll finish chapter 2 today, and then there's assignment 2 and assignment 3. Those are just regular assignments. Those are both going to be due next Thursday on the 25th. Okay? And then the Excel assignments 2 and 3, one's for numerical, one's for categorical. I'd like to keep them separate, are both due on the 30th, which is a holiday, I know, so that's rude, but I can only do it so far. So, and I did post this little clip from Superstore, but you'll have to wait until the perfect moment where I can bring it up. But okay, we can watch it now. I can never get the sound to work properly. Anyways, so Superstore is kind of riddled with stats jokes if you kind of know what to look for. And so, but this one I thought was so good. I'm standing in front of my TV. I couldn't find the clip anywhere, and I'm probably just maybe too old. So I just decided to film it with my phone. It's truly pirated. So you're welcome. That's how important it was to me. Now, hopefully the sound is good. Wait, turn it on. I don't know. All right.
Literally be surrounded by killers?
Uh-oh.
You don't think people in this store do marijuana, do you?
Maybe here.
I mean,
Good thing I have subtitles on.
Probably.
How many of them?
Like half.
Half. Wait, half do or half don't?
It's both.
Both?
okay.
So, anyways, it's there. You can watch it. I know the sound was weird. Anyways, you'll have to wait until I bring it up again. But now you know. Half do or half don't? Well, both. Okay. So, last day, it was just on Tuesday. We don't really need to do a ton of review because it was just mere moments ago. Right? But we did introduce, well, we talked about a lot of things, but then where we finished was we talked about the median, right? The median as our measure of center. If we have a non-normal distribution, it's a better measure of center than the mean. Okay? And so, and we'll see why again in a little bit, but we did mention it's robust to outliers, right? So for example, if we change this to 370, right, compared to the rest of the data set, that's an outlier that's extreme, right? Not really what we would expect to see in this group of data points, right? But the median doesn't care about that, just uses it as a data point, and it still finds the central value of 32, which is our median, right? And so our median, I'll erase this because there, it's not what was there before, but so the median is just the value that splits your data in half. Okay, there are kind of two ways to get the median, right? And so it either is the value, right? It is the 32 here, so then the median is 32. Okay? When we find the quartiles, because we use this 32 as the median, we do not use it. It's already been used up. Okay? And so then to find the quartiles, what we do, which is really just the median again, but with the lower half, right? Really what we do is we start at the next data point down, right? So now our quartiles, remember, are splitting our data into quarters. Right? So then we start our boop, boop, boop at 21 and 29, and we land on 27. If you ever land on two values at the same time, you take the average of the two. Just like here. So here we found the median, and the median is at this line now. And so we found that the average of these two, 29 and 32, is 30 and a half. So that is our median in this case. And I'll do a same kind of notice. The median, oops. I'll start down here. The median is at the line drawn which means we use 29 and 32 in finding their respective quartiles. So slightly different, which means we use 29 and 32 to find their respective quartiles. We use 29 to find Q1, right? And so 29 and 5, I wish I could have 2 pointers, but I guess that would be hard. And so, all right, remember our boop, boop, boop? And so we boop at the same time. And now I've landed on 21 and 27, right? And so what that means is that Q1 is 21 plus 27 divided by 2. Where's my trusty calculator? 21 plus 27 divided by 2, I get 24. So then my first quartile is 24. And as I mentioned, if you're using the Excel functions for the median and the quartiles, right, they use slightly more sophisticated weighting than the average, right? So the numbers might be slightly off, but as long as they're kind of close. Right? And on the test, I expect you to use this method, right? Because you won't have Excel. So that simplifies things, I guess. about Q3? 32 and 37. One. Boop, boop. I'll do it up here. Q3, the third quartile, which means what? It means it has 3/4 of the data below it, and then the last quarter above it. Okay. Q3 is 34 plus 34 divided by 2, which I'm going to go ahead and say is 34. That one's nice. Okay. Why do we need the quartiles? You said the quartiles. Well, we use the quartiles to find the interquartile range, right? And so for non-normal distributions, we use the interquartile range as our measure of spread. We use the interquartile range. Which we abbreviate IQR as our measure of spread. The interquartile range IQR is Q3 minus Q1. So on a test, yeah. Booping?
Yeah.
No, any larger data sets you would use Excel and just rely on Excel. I'm sure there are, but you'd still have to, it would only give you the location of it, and you'd still have to count in. So doesn't save you a ton of time. But I'll give you a maximum of 12 data points, I think it is. So nothing crazy. This is 1, 2, 3, 4, 5, 6, 7, 8. Makes it a little bit more interesting with 4 more, but not that spicy. Okay. So the interquartile, oh, that's what I was saying. So on a test, I will not make you calculate the mean and the standard deviation. Right? I don't feel bad making you calculate the mean, but I won't make you calculate the standard deviation. How about that? Right? Because it's hard, it's long and boring. Once you've done it enough. I will make you find the median and the quartiles. Okay? And so that's kind of the little bit of calculation that I'll make you do. Okay? But that's about it. Okay? And that's because later, right, for the interquartile range, you need Q3 and you need Q1. The interquartile range is what? Well, it's the distance between the central 50% of your data. Right? And so it kind of ignores the tails and just talks about, okay, well, how tight, essentially, is the central 50% of your data? Right? If it's spread out, then there's a lot of spread, and that gives you a large IQR, right? Or if it's really tight, then you have a small IQR. And so, let's see here. So the IQR, recall, the IQR is the distance I'll say covered by the central 50% of the data. A really common numerical summary that we do is called a 5-number summary. And so the 5-number summary is a common way to summarize data numerically. To summarize data numerically, and it looks like this. I just need 5 lines. That shouldn't be a surprise because it's a 5-number summary. I'll highlight it though, that I smooshed it in here. So the 5-number summary is going to look like this. You start with your minimum. Then you list your Q1. Then you list your median. Then your Q3. And then your maximum. Usually I just use shorthand, but I'm trying to be proper. This is what we call the 5-number summary. They have to be in this order because a trained eye would be able to look at these values and evaluate the distances between them and then be able to figure out what the shape of the distribution is. That takes a lot of practice, right? But for us, it's really just a way of me getting to ask you, hey, do you know how to find the median? Do you know how to find the quartiles? And then list them nicely. Okay? So you want to start from the smallest value, and then you move to your first quartile, and then your median, and then your third quartile, and then your maximum. Okay? Yeah. It's the largest value. Yeah. And the minimum is the smallest value. So in this case, 5 would be your minimum, and 37 would be your maximum. Okay? And your Q1, you would list as 24. Your median was 30 and a half, and your Q3 was 34. Gets confusing because we had 2 examples here, which would each have a 5-number summary. Let's, as an example, use the second data set above. This one, so I don't have to scroll so far. And maybe I can, oh, I'll try to draw that one. Ugh. I like to do my minimum and my maximum. They're quick wins, right? 537. Let's jot those down. If you're starting from scratch, right, of course, you'd have to sort your data from smallest to largest before you find your minimum and your maximums. But then the next step would be to find your median, which we did. So you can write it down as 30 and a half. From your median, you need your median, right? Because you need to know how your median behaves in order to find your quartiles. But once you have your median, you're off to the races. And we found 24 and 34. from here, we can also find that the interquartile range, which is Q3 minus Q1, is 34 minus 24, which is 10. That's nice. So even though our overall data went a distance of 32, right, between 5 and 37, the central 50% of our data, even though it's a small data set, so it gets kind of weird, but the central 50% of the data, right, happened in the span of just 10, right? The interquartile range is 10, from 24 to 34. Right? So a lot of activity in that range. So on test one, I'm going to give you a data set, right? Just like here. And instead of asking you find the median, find the quartiles, I'll just say find the 5-number summary, right? Which means you have to do all those things, right? But it also means you have to remember what the 5-number summary is, right? But there it is. Now the box plot is a visual representation of the 5-number summary. I always find that it's a little bit easier. So a box plot sounds like it might have a box in it, and it does. And so I just find it easier to show you what a box plot looks like, and then we'll talk about it. So this box is the central 50% of your data. Okay? And so this is a data set. We don't know what the underlying data set is. It's being visualized with the box plot. Okay? Oh, it looks like it's number of study hours per week, but I don't know how many data points I have or anything like that. That's okay. So what's the key components here? This thick line in the middle of the box is the median. And so we start there. Bless you. The data is increasing from the bottom going up, right? And so this seems to be my minimum. And if you kind of had to guess what these points are, they feel like outliers. They look like outliers, right? And we'll see why in just a moment, but they are outliers. So let's just get those out of the way here. So we indicate the outliers with just individual dots, and that also means on the lower end here, there are no outliers. These little guys, you can call them fences, or I like to call them whiskers is another term for them. And I think it's just way cuter. And so these two things are whiskers. So those whiskers go some set distance, and we'll learn how far in just a moment. And then they reach a certain point, and then we say, okay, after that point, these guys are outliers. In fact, I think we're ready for it. This must be Q1, because we said the box is the central 50% of the data, right? And so Q1 And this must be Q3. Now, what's special about the whiskers is they're going to extend as far down from Q1 as Q1 minus 1.5 times the interquartile range. So we take this range, this distance of the quartiles, right, the interquartile range, and then it was just decided a long, long time ago that 1.5 is a reasonable number to multiply that by. There are other rules, but we don't really use them. Okay, so the most commonly used rule that we use is 1.5, which is why it's called the 1.5 IQR rule. Okay? And so here, the lower whisker extends to the minimum or Q1 minus 1.5 times the interquartile range, whichever comes first. Whichever comes first. I'm not going to make you construct a box plot, but you do have to be able to read box plots. And so there's a lot of in and outs, but once you get used to it, it's okay. This distance here is the interquartile range, which you find by Q3 minus Q1 still. So because this lower whisker just ends and there are no points beyond it, right, then we know that this is also the minimum. Weird. Whereas the upper whisker has the same rule. The upper whisker extends to the maximum data point, or now we're moving up from Q3. So notice how the lower whisker goes from Q1, and I want to go and figure out how far can I go lower before it's considered an outlier. Okay. And then the upper whisker extends from Q3. So now it's going to be Q3, but up from Q3. So now it's plus 1.5 times the interquartile range, whichever comes first. That takes some practice. Technically, it goes to the data point inside the whisker, but that's picky. And then anything outside of the 1.5 IQR is considered an outlier.
Is the 1.5 times IQR?
Yeah. Yeah, I should have put some brackets on here. So it's 1.5. So it's the interquartile range times 1.5. Just statisticians way back in the day. I imagine them sitting in a room saying, well, what about 2? No, you won't see any activity. Yeah. I think another one that I've seen around is 1.7. Someone probably got a PhD for it. I decided to try it with 1.7 and it works. Wow, crazy. There was some low-hanging fruit back in the day. Not so much anymore. So it is arbitrary, but it is the value that we use. All right. So it's the same, but I like to draw it out so we can talk about it. But then here's a nicer, a nicer summary of it. And so, what does it mean to have a larger distance? Right, this longer distance here means it took a longer time in terms of covering data to cover this 25%, right? Technically, the last 25% is from Q3 all the way to the maximum, right? So it takes a long time to get there, which means there's not very much data, right? Whereas if you have a kind of a tight distance, then it didn't take very long to cover that quarter of the data, right? And I think, let me just make sure that I have, oh wow, it's not for a while. Okay, I'm just gonna draw it. Huh? And so a long distance between quartiles, and by that I mean kind of Q1, Q2, Q3, Q4, right? Between quartiles indicates there is not much data there. It's the same amount of data, but if you think about something, and I'm going to draw my box plot on the slide like this. Ooh, crazy. That's okay. Just means that my measurements will be on the x-axis instead of the y. So from a box plot, and there are no suspected outliers here, no dots. It's just everything is in the box plot and the whiskers. What we know about the box plot is that this is the median, right? And so at this point, right, I've already covered 50% of my data, right? Which means a ton of data points happened in this tiny range, right? So here's 50% of my data, but then for the remainder, it took me that long to cover the remaining 50% of the data. Now, I think that it's a little bit difficult to look at that and figure out, well, what is the distribution? So, but what it would look like is something like this, right? Where very quickly you would cover the 50%, and then it would take you a long time to cover the remaining 50%. Right? So this is what a skewed distribution looks like as a box plot. Versus a normal distribution. A normal distribution as a box plot, you would start with your box, and there would be some symmetry there. Your median is in the center because it's symmetric around the mode. And I should make my box a little bit smaller because we tend to have longer whiskers for a normal distribution. But notice how it's still symmetric around the median, right? And so it's symmetric, but we cover the 50% of the data pretty rapidly, but then the remaining, those tails, take a longer time. And so this would end up looking like this. Nice. Here's a fun fact. In a normal distribution, the mean is usually equal to the median or roughly equal to the median. So here, the mean is going to be roughly the median in a normal distribution. So in theory, right, you could use the median as your measure of center for a normal distribution. It's just that the mean has a lot more tools associated with it, right? So if we can use the mean, then we should, okay? But they'll be roughly the same, right? Which means what? It means if you have the mean and the median, and you look at them and you consider them basically the same, then that tells you that the distribution is likely normal, right? So that's kind of cool. Back to outliers. So as we said, the whiskers of the box plot can extend up to 1.5 times the interquartile range away from the quartiles, right? And that away is kind of tricky, right? Because for the max whisker reach, we go up from Q3, right? And I find the visual kind of helpful. If you have Q3 and then you want to move up for your whisker, right? So then you have to add it, and I'll toss brackets around here as well. Whereas the lower whisker goes down from Q1. So now I have Q1 minus 1.5 times the interquartile range, which I'll also wrap up in brackets. So if we have this made up Q3, Q1, the interquartile of 20 and 10, for example, right? The interquartile range would be 10. 1.5 times 10 is 15. So my max upper reach, or my max whisker, or my upper whisker is what I like to call it, is going to be Q3 plus 1.5 times the interquartile range, which is 35. What this means is any value in your data set larger than 35 is considered an outlier. So here, any value in your data larger than 35 is an outlier. And of course, by symmetry, if the lower bound is -5, then any data point less than -5 is considered an outlier. I'll write it, even though it seems redundant. Any value in your data less than -5 is an outlier. Why do we care about outliers? Well, that should be obvious, hopefully. But it does help us identify any skew that we might have. It also helps us identify maybe data collection or entry errors, right? If something like you see a 370, but you think that maybe it should have been a 37, right? then you ideally can go back and check to see if that makes sense, and then maybe you can change it, right? Or it might actually show you interesting features in your data. That's not usually what happens, but. So how would sample statistics like the mean, the median, the standard deviation, and the interquartile range of household income be affected if the largest value is replaced by $10 million? What if the smallest value is replaced by 10 million? So here we have the annual household income. It is skewed. Just like we know about money, money is usually skewed to the right. And so what this question is really asking you to think about is, okay, well, the median, and I'm just going to go ahead and tell you, the median would be somewhere around here. Whereas, and maybe I'll just make it a little bit bigger. You could even count all the points, figure out where the halfway mark is, right? And then that's where the median would be. But I would guesstimate that it would be somewhere around there. Whereas the mean might be somewhere out here. So the mean is always pulled in the direction of the tail. And so the mean is always pulled in the direction of the tail. So if you have a distribution like this, then the median just kind of holds steady at the center, but the mean would be in the lower tail, right? So if you have numbers for the mean and the median, right, you can compare the two to see, well, what shape would I expect this to have? And we already mentioned it, but I may as well put it here as well. If I have a symmetric distribution and a normal distribution, then the median is going to be roughly equal to the mean. That's kind of a neat trick. So you can compare those two values and see, well, how do they compare? If the mean is less than the median, right, then you know it's being pulled in the tail, so start where the tail is, and then you can visualize your distribution. Right? Nice. I'll highlight this because that's the important part they need to remember to kind of compare the mean and the median to get to a distribution. So we've already introduced this idea of robust statistics last day, right? But as we saw earlier here too, right, the median is just hanging out at the peak-ish, right? And so it is a reasonable measure of center, right? And so, because it doesn't care about these outlying values, right? So they've done some calculations where they have the original data of the annual household income, and then they made some moves, moved the largest to 10 million, moved the smallest to 10 million, and you see some slight changes in the median, right? 190 to 200, okay, fine. because the smallest was moved to a large value. Fair enough. But the interquartile range stays the same, whereas the mean x bar, remember, is all over the map. Right? And so 245, 309, 316, and so it's hugely influenced by these minor changes. Right? And I'll say robust to outliers. Huh? These are not robust to outliers because they are influenced by minor changes in the data. Huh? So they only are really good if you have a normal distribution. But like I said, luckily we have a normal distribution a lot of the time. So that's great. Okay. So like we said, for skewed distributions, it's often more helpful to use the median and the interquartile range to describe the center and spread. And for symmetric distributions, then we can go ahead and use the mean and the standard deviation. The standard deviation is linked to it, to the mean, because we use the mean in our calculation, right? So if our mean is being pulled, then our standard deviation is going to kind of be pulled along as well and be ruined. If you would like to estimate the typical household income for a student, would you be more interested in the mean or the median income? I'm going to go ahead and say the median because any sort of money data is skewed. Since the distribution, distribution is likely skewed. We actually already talked about this, but if the distribution is symmetric, then the mean is roughly equal to the median. I like to think of it as just pulling the mean towards the tail. Right, wherever you've got a tail, the mean is going to go there. Okay. Which is most likely true for the distribution of percentage of time actually spent taking notes in class versus on Facebook, Twitter, etc. Well, I know you guys aren't on either of those, but etc. That's you guys. This looks like a skewed distribution, right? Something like this. Which means that, okay, well then we know that the median is roughly around the peak, right? It'll be a little bit off, but not too far. And the mean would be somewhere pulled in the direction of the tail. Right? So here, the mean is less than the median. And so the mean is less than the median. This less than, color can I use? Light green, maybe, is this guy. Right. I always really struggled with the alligator eats the big one because I would just overthink it. Am I the alligator or what? But this makes an L, right? Kind of make your left hand L, right? That's how you know it's your left hand. And then you can just read it as the mean is less than the median, right? And so what we're going to say here is the mean is less than the median. And what's funny, this is one of those where it wasn't until I was teaching a class and I said, "Oh, who understands that alligator eats the big one stuff?" But anyways, here's the sign. I just memorized it. And then I had a student who was like, it just makes an L, right? So I like to throw that in there. Yeah, but I have the same problem. Am I Pac-Man? I don't know why I struggle with it so much, but I do. And it's okay. I survived. Even got a math degree. So, ha. Well, I just memorized it. So which one is it? It looks like C to me. Ta-da. Nice. Pac-Man, alligator. Oh. Cute, but not for me. If you have extremely skewed data, one of the options that you'll have in working with your data that we won't pursue any further than the next couple of slides, but if you are in biology, for example, it's really common to do log transformations, and so I just want to introduce them here, but then we'll just forget all about it, right? But if you see a log transformation, I know physics does log transformations as well, right? They're very common if you have very skewed distributions. Do you remember logs? Exponents and logs? Don't worry. It's just a log button on your calculator. And I know what you're wondering. Log base E or log base 10? Oh, don't worry about that. Doesn't matter. Here, and they forgot a critical component of this example. This is the log of the number of basketball games attended. And so here's our original data, which we can zoom in, and there are some data points down here all the way along, but not very many. Right? And so it does stretch that far, but we have this extremely skewed distribution of data. Okay. Now, if I take the log and I transform that data, so I take the log of each individual observation, okay, and you would just do it in Excel anyways. Type in log, take the log of each number, done. Then all of a sudden we have this way more reasonable looking distribution. Right? I wouldn't call it normal, but it's getting there. Right? In fact, a lot of the time what happens when you do a log transformation is it becomes normal. And the only problem is when you have to interpret it, you're interpreting the log of the data, and that's really kind of difficult to do. And so for us, we leave it here, but so for example, the number of games is 70. If you take the log of 70, you get 4.25, right? And so it's really just kind of transforming each data point by taking the log of it. Okay? But what I wanted to highlight on this is that it's really hard to talk about the log of the number of games, for example. Right? It's hard to communicate information about. And let's not do this one. We can move on. Phew. I thought it was 5 for a second. But we have to finish chapter 2 today. I already bumped the start of chapter 3 till next week. It's a Tuesday us kind of problem. I don't know why they threw intensity maps here, but it is another way to visualize data, visualize numerical data. And no doubt you've seen intensity maps, or we call them heat maps sometimes. They were all the rage at one point when they kind of first started being easy to generate. Now they're super easy to generate, so everyone's doing them. But of course, the color in an area indicates the change in population since 2000. And it's just a data visualization. Like I said, I'm not entirely sure why it's in here, but forgot to cut it, so oh well. Numerical data, it's a biggie. Luckily, categorical data and kind of summarizing categorical data and visualizing categorical data, there isn't a whole lot that we can do. But that's what we're going to do now. And so, just like before, we're going to talk about, well, how can I visualize categorical data? And how can I summarize categorical data? So we're going to visualize, bless you, and summarize numerically. We have lots of options. So if we go back to our numerical data, right, in terms of visualizing, we introduced a couple of options, but then we landed on just a histogram, right? Even a box plot, I traced it back to what a histogram might look like for the box plot. And so there's really only one. But for summarizing numerical data, right, well, it depended on the shape, the mean and the standard deviation for normal distributions, or the median and the interquartile range for non-normal distributions, right? There was a lot of ground to cover, right? And then we introduced the 1.5 times the interquartile range rule for outliers, right? Just sprinkle that in there. Categorical data, way less interesting. What's a categorical variable? Well, it's any variable that you can put into categories, of course. Right? Car color. Right? What year of school are you in? First year, second year, third year, fourth year, fifth year. Right? Victory lap. And so, but there's not going to be a lot that we can do with categorical data. Contingency tables, we're just jumping right in. You've probably seen a contingency table or two in the past, something like this. This is kind of a funny / weird example, but we've got the distribution. So it's still talking about the distribution, but distribution across categories, right? The distribution of students' genders and whether or not they're looking for a spouse while in college. They want that MRS degree, I guess. Like I said, weird example, but whatever, we've got some numbers. So, gender, we keep it simple, right? Just binary, male, female, obviously others, but you'll find all these examples are just binary. The only upside of that is it makes the math really a lot simpler. So it's the upside. Whether they're looking for a spouse, no or yes. And then we have totals. Sometimes you have to add up and find the totals yourselves, but these totals are different depending on which category I'm talking about. Right? This 137 tells me that there were 137 females in the sample. Right? This 70 tells me that there were 70 males in the sample. So quite different sample sizes here. Right? Okay. Looking for a spouse, 138, regardless of gender, said no. And 69, regardless of gender, said yes. Right? This is our grand total. Right? This is our sample size. N is 207. So the survey surveyed 207 students. So this is what we call a contingency table. It's just a table, a summary of counts. Okay. How do we read the inside values? This 86 is the number of females who were not looking for a spouse. Right? And so this is females and not looking for a spouse. And what color haven't I used? Maybe this one here. 86 females and not looking for a spouse. Notice how I really emphasize that and, right? Because it's the overlap. Right? What's this 18? There were 18 students that were males and looking for a spouse out of 207, right? Of the total students. Or what else could you be interested in? Well, of the males, how many were looking for a spouse? Well, of the males, there were only 70 males. Right? So now 18 of those 70 were looking for males, or looking for a spouse. Oh. Words. So there's a lot that you can find using this table, but constructing this table is not too bad. Right? Even though we immediately leveled up and introduced two categorical variables. Right? What would one categorical variable look like? Well, if you're just talking about the looking for a spouse, you would just be, I guess not even the central part. Sorry. It would be this, right? Looking for a spouse? No, 138. Yes, 69. Right. But that's pretty boring. I'll erase that for now. Wait. Oh. Fine, I'll put it on here. Versus a table, or I'll call it a contingency table. Although technically a contingency table is a two-way table. So maybe I'll say a summary of one variable might be something like this, looking for a spouse. That's my variable. My categories are no and yes. and I had 138 no's and 69 yeses. But you can see how boring that is. It's just one variable, right? So really we're just talking about counts in each category. To visualize a categorical variable, we can use bar plots to visualize categorical variables. At first glance, these two graphs look the same, right? Just as the name suggests, there are bars, right? Bars of different heights representing how many counts I had in each category, right? And the categories are listed down here, female and male. So it'll look very similar to a histogram, except there should always be a space to indicate that, hey, these are categories, right? And of course, the categories should be listed below the bars. What's the difference between the first one and the second one? Well, we'd have to focus in on the axis, right? Here we have the raw counts on the first one, and here we have the proportions. And so here, this is what we call a relative frequency bar plot with the proportions versus the raw counts. Notice that they look the same, but the proportions are going to be more useful later on. Here's a spoiler alert. A proportion is a probability, which I think you suspected we might be talking about in this course, and you'd be right. As early as next week. Probability. And both of those, so we can use those two words interchangeably. They're also roughly equal to a percentage, right? Where we just multiply by 100. That's why it's roughly equal, because it's you have to multiply by 100, right? But if we look at something like 0.6, your brain probably just automatically thinks 60%, right? Because proportions are between 0 and 1, right? And percentages, you just multiply by 100, right? So 0.6 is 60%, for example. How are bar plots different than histograms? Well, we're talking about categorical variables, so that's a huge difference. But versus histograms, which are for numerical variables. But the x-axis is going to tell the story. And so whatever's on the x-axis is going to indicate to you whether you have a numerical variable or a categorical variable with multiple categories. The categories can be listed in any order, although if you have an ordinal variable, right, where there's some natural ordering, usually we try to impose that ordering. But what if we wanted to answer a question like, does there appear to be a relationship between gender and whether the student is looking for a spouse in college? Now, what you would want to consider is, especially because we had 137 females and 70 males, right? So we need to take those different counts into account, I guess. So what we want to do is we want to find the percentage of females looking for a spouse. which is this 51 out of 137, which is roughly 0.37, right? Or 37%. I'm going to insert a key word here. Percent of females, which is 37%. Since it asks for the percentage, we should probably do the percentage. Percentage of males looking for a spouse is roughly 26%, right? 18 out of 70. So notice this, the percentage of females, of males, tells me what to use in my denominator, right? Whereas if I just wanted to know what percentage of students, right, were looking for a spouse, then I'd have this 69 over 207 versus percentage of students looking for a spouse is 69 out of 207, which is roughly, let's see, a third, or 0.33 repeating, or roughly 33%. We're going to have methods of comparing these values and determining if they actually are different from each other. Of course, 26 is not the same as 37, right? But are they far enough away from each other that I would feel comfortable saying there is a difference between how males and females feel, I guess. I don't know. Right. And at this point, it's really just kind of how you feel about the difference between 26 and 37. If you feel like that's a big difference, then yeah, you would say that there's a difference. For me, not really. There's some wiggle room there, but we'll have to wait a couple of weeks until we have a method of mathematically comparing these two percentages. But we will. And isn't that exciting? Wow. If you want to visualize two categorical variables, you've got a couple of options. Yeah. And they're all readily available in Excel. And so we'll just talk about them here. You've got the stacked bar plot, which stacks categories inside the bars. Side-by-side bar plot puts them side by side, lumped by categories. There's a standardized stacked bar plot, which is on that proportional scale, right? And so they're not doing anything crazy. I don't love mosaic plots. This is a mosaic plot. I don't tend to use them because I find that they are not very intuitive, right? I'm going to take some time to see what's going on with this mosaic plot. So this is a stacked bar chart. The first one is a stacked bar chart. Good. This, what did we call it? Standardized. And this is a mosaic. They all show the exact same data, just in different ways. And so depending on your audience or what you want to emphasize, right, then I always like the standard, just stacked bar chart. What's the difference between the stacked bar chart and this one here? Now, the bars are the same height, right? And so now each bar is talking about all the females versus all the males, right? And it doesn't actually show that there were fewer males than females, right? So we've kind of lost that information. But if you're comparing, right, your males and your females, then this one is a better way to go, I guess. And now for the mosaic, this is why I don't like it, is because the width of the bars also gives you information, right? And so there were fewer males, and so the bar is not as wide. But of those males, more answered no than yes. And then the width of the female bar tells me that there were more females in the sample. Wider means more females in the sample. Here's some Titanic data, kind of a typical data set. You've done any sort of kind of poking around, how to learn stats, how to learn data science. They always start off with a Titanic data set, and it's got a ton of information. It's a nice big data set. There's some missing data, and it's just kind of a nice starter data set. And of course, they have the age of the passenger, right? And so we've divvied them up into adults or child, right? By the mosaic plot, we can see that there actually weren't that many children because it was probably really expensive, right? And so, right, very few children, very many adults, right? But in terms of the distribution of how many died and how many survived within each age category, right, we can compare the two. A lot more of the children survived than the adults. I should hope so, because what kind of an adult would say, oh, get out of here, I'm going in that life raft, to a child? That's crazy. I would say this bar should probably be a little bit higher, a little bit embarrassing. Anyways, so, oh, I should ask, any questions so far? No. Pie charts are bad. And I know. I'll even do it in red. Bad. I know. Everyone loves a pie chart. But the problem with pie charts is, well, there's a lot of trouble with pie charts. There's been a lot of research on how our brains kind of process information. Okay? And these slices are really difficult for us to differentiate in size, right? And so if you had to focus on, there's some that, I don't know, you can kind of tell, obviously this yellow one is smaller than this yellow slice, but just using the same color over again is a problem, right? And so pie charts, pie charts, right? The problem is we can't see the size of the slice. That's hard to say, right? Easily, unless it's very, very obvious. Whereas here, let's go back to one. All right. If we have bars, even if the bars are almost the same height, our eyes do a good job of saying this one's slightly smaller, right? And so it's easier to determine the difference in the sizes, right? Difference in counts, which is our goal. Right? And so that's one thing about pie charts. Let's write that down. So what can I say? How can I summarize it? It is often difficult to see or to compare, that's what I should say, to compare two slices in a pie for size. Oops. Whereas if we compare it to just some bars, immediately your eye can tell that this one is just slightly smaller, right? That's really hard to do in a pie. Huh? I would say the only time a pie chart is obvious is if you only have two categories, right? So the only time a pie chart is obvious is with two slices. Those slices are really categories. Two slices are categories. But if I tell you that 70% of students get an A in this course, what does your brain do? Then you also know what percentage doesn't get an A in this course. 30. So then there's two categories. You get an A in this course or you don't get an A in this course. That's two categories, right? Yes, no. But knowing one number tells me about the other number, right? And so in that scenario, just a number would suffice, right? And so the only time a pie chart is obvious is with two slices or categories, period. In this case, just the number would suffice. That is 70% will get an A in this course, for example. Shouldn't say that is the EX. For example, 70% will get an A in this course. Right. Then we know 30% won't, for example. I should look at what the number is. That might be more fun. But then, I know, it's a roundabout way of bringing in the Superstore clip. But if half do, then you also know that half don't. Right? And so pie charts, try not to use them. I know a lot of very high up analysts still use pie charts, but don't be one of them. I should say, our eyes can't really handle it. What if we do a mashup? This, right? Numerical data, across groups. Well, groups are categorical variables. We can do a combination of the two, right? And so what we usually have, can't scroll too high, because I've got a funny. Here I have a categorical variable. Does there appear to be a relationship between class year and the number of clubs students are in? This, I can never, okay, fine. I have to show you this terrible quality image. So Marshall's made a pie chart of his favorite bars and a bar chart of his favorite pies. It makes no sense if you really try to dig deep, because you can only have one favorite. Anyways, must be a survey of favorite bars and favorite pies. Anyways, that's not what it's about. This is a categorical variable. But here we have a numerical variable. So for each category, we tend to generate a box plot, right? Mostly because it's really hard to, you can kind of layer histograms on top of each other, but it gets really hard to compare values. And so for that reason, we tend to use a box plot instead. If you want to compare these distributions, what do you really want to do? You want to compare these box plots across the categories, right? And so one thing that I would do is I would focus on the median, start there. And it tends to kind of hover around, I don't know what the number of clubs the students are in. It can go as high as what looks to be kind of around 3, but it seems to hover between 2 and 3 for all the age groups. Okay, so relatively the same, I would say. You can compare the minimums, right? Here's an outlier, but slightly higher just in general for the juniors, right? The sophomore and the juniors. And then you've got some outliers in those sophomores and juniors. You can look at the width of the box plot. What does it mean when the median is also at Q1? I mean, 25% of the data was exactly the same, right? Picking up from Q1, it looks like it was about 2 up to the median, just 2, 2, 2, 2, 2, 2, 2. All right. Same thing here. Looks like 3, 3, 3, 3 from the median all the way up to Q3. Okay. Same thing for the seniors. There's no downward whisker, which means that the minimum is also the same as Q1, right? Which means all your first data points were at 1 here. All right. It's your lucky day, because that's the end of chapter 2. Try reading chapter 3 before, because I did push it off from today to next week. So we'll have to go a little bit harder, not too much, but. And enjoy your weekend. That's important.